Okay, this is chapter 1 homework for Physics 201. It says carry out the following arithmetic operations. The sum of the measured values 756, 37.2, 0.83, and 2.5. When we add up numbers, we keep the lowest number of decimal places. So when I add up these numbers, I will say 756 plus 37.2 plus 0.83 plus 2.5. And if I just put those in my calculator, I get 796.53. But the lowest number of decimal places is with this number, so I keep 0 decimal places. So I'm going to round that up to 797. In part B, we want to know the product of 0.0032 times 356.3, and with multiplication we keep the lowest number of sig figs. Alright, so if I put this in my calculator, I get 1.14016. Alright, but I have 2 significant figures on this one and 4 on this one, so I just keep 2 sig figs. That's 1.1. Part C, the product of 5.620 times pi. Pi has an infinite number known digit, so we don't consider it when we consider our significant figures. The lowest number of sig figs in this case is with this number, and it has 4 sig figs. If we put this in our calculator, we get 17.65575. And keeping 4 sig figs, I get 17.66. And then finally in part D, I will do this operation first, keeping 3 sig figs, keeping the lowest number of sig figs. So it's going to be 8.69 divided by 3.2 plus 2.32. Now I'm going to do this operation, keeping the lowest number of sig figs, which is 2 because of 3.2. And so that's equal to 2.7, again with 2 significant figures, plus 2.32. And then I will add those 2 numbers together. So I do my multiplication and division first, and then I do my addition and subtraction. I keep 1 decimal place, the lowest number of decimals for addition and subtraction. That's 1 decimal place, and so I get 5.0. And so that is the correct answer. All right, there are a couple of different ways in doing these order of operations. You can just keep a lot of significant figures right up until the very end in order to, and then determine how many sig figs you keep, or you can do it step by step. And either way is correct, I think, and I will accept either in the class. All right, the population density of Los Angeles is about 4,000 people per kilometer squared. Now what that means is that if I have a kilometer square, this is 1 kilometer, this is 1 kilometer, 1 square kilometer, it means that there are on average 4,000 people in that square. All right, and we're assuming that they're all equidistant apart. I want to know how far apart are those people. Now the point of this exercise or this problem is just to help you work with units, and in this chapter you work with units a lot. So this is just an exercise to help you work with units. All right, so I have 4,000 people. Let's do Los Angeles first, LA. So I have 4,000 people per kilometer squared. All right, people aren't really a unit, so I'll just do per kilometer squared. That means that each person occupies 1/4,000th of a square kilometer. Each person occupies 1/4,000th of a square kilometer. That means that this person occupies a space that's equal to 1/4,000th of a square kilometer. So this space right here of that one person is 1/4,000th of a square kilometer. All right, so that's the area. Now that is equal to 2.5 times 10 to the minus 4. Just doing that division. That's in square kilometers. All right. And now that's the area. I want to know the length of the side. So if I have this, if I take this and blow it up, this is the space that one person occupies, and it is 2.5 times 10 to the minus 4. That's the area that it occupies. And I want to know what is this distance. All right, what I'll call this distance L. Area is equal to length squared. So length is equal to the square root of the area. So that distance L is the square root of 2.5 times 10 to the minus 4. That's square kilometers. And then that gives me the distance on the side of the area of each person. So that is going to be 0.016 kilometers. And I can convert that into meters, which is more appropriate, 16 meters. That means that in Los Angeles, if you were to equally distribute every person, there would be 16 meters between each person, right? Just based on that population density. All right, so now we can do a similar thing with San Francisco. All right, with San Francisco, it has a bigger population density, so it should be smaller. So I have the area that each person occupies is 1 over 6,000 square kilometers. That's 1.7 times 10 to the minus 4 square kilometers. And then if I want to find the length, that's the square root of that area. And that's equal to 0.013 kilometers, which is equal to 13 meters. All right, so that's the separation in San Francisco. If you were to lay them out equidistant, every person equidistant from from the person next to them, they would be 13 meters apart. Now, I want to know how many times further away is the average person's nearest neighbor in Los Angeles than in San Francisco. So we just take the ratio of these two. We just say 16 meters over 13 meters. In Los Angeles, a person is 1.2 times farther away than in San Francisco. All right. Again, it's just working with units and knowing what units mean and being able to work with these sort of basic units in area and length and doing unit conversions and what have you. All right, a house is 50 foot long by 26 feet wide by 8 foot high ceilings. What is the volume of the interior of the house in cubic meters and in cubic centimeters? All right, so I will give you this conversion factor, and that is that 1 meter is 3.28 feet. Meter is slightly bigger than a yard by about a few inches, about a quarter of a foot. All right, so let's just go ahead and calculate the volume of the house in feet. Volume is length times width times height. That's going to be 50 times 26 times 8. And if I multiply those out, I get 10,000 cubic feet. Actually, let's see, I think I get like 10,400 or something. Yeah, I get 10,400 cubic feet, but I want to keep the lowest number of sig figs, so that's 2. So I'm going to keep just 10,000 cubic feet. All right. Now, we need to be clear here that actually I have 2 sig figs in this number. It just so happens that one of those is a 0. You won't encounter this very often. I think usually in math circles they put a bar over it. So that second digit is actually a significant digit. We'll need to remember that in just a moment. All right. So we want to convert this now into cubic meters. So I say 10,000 cubic feet. And then I just do a unit conversion factor. I'm going to do a unit conversion factor. I should have feet in the denominator because these feet are going to cancel with these feet. And then meters in the numerator. So I just take my unit conversion up here. 1 meter is 3.28 feet. but notice that the feet don't cancel out. That's because I need to cube this whole term. So 10,000 over 3.28 cubed, that's 290 cubic meters. And notice that I'm keeping two significant figures here because I had two significant figures here and here. All right, you don't consider the significant digits of these numbers because it's a conversion factor, and you assume that you know the numbers perfectly well. Okay, so now I also want to convert that to centimeters. I'm going to convert cubic meters to cubic centimeters. 290 cubic meters. I need to do a conversion factor. Now, you need to know the metric prefixes, and in particular, we'll use centimeters a lot. And you can say that 1 centimeter is equal to 10 to the minus 2 meters. Another way of thinking about this is that 1 meter is equal to 100 centimeters. Right? And that will give you two different ways of working through this. 290 cubic meters in 1 centimeter. There are 10 to the minus 2 meters. And then we want to cube that. All right. So what we're doing here is we're basically multiplying this number 290 by 1, right? Because 1 centimeter is equal to 10 to the minus 2 meters. So if we divide the two, then they're effectively multiplying it by 1, but with different units. All right, so that gives us 2.9 times 10 to the 8. Cubic centimeters. As I said, there's another way, and I usually do it this way just because it's the way I think, and that is that there are 100 centimeters in 1 meter, and then cube that, and that gives you the same 2.9 times 10 to the 8 cubic centimeters. All right, so those are the answers. Very likely to see unit conversions embedded within problems on the exams where you have to convert from one unit to another unit. That's fairly common in any technical or scientific field. So for the triangle shown in this figure, what are the length of the unknown side, the angle theta, the sine theta, and the tangent of theta? All right, so just remind you of our mnemonic SOHCAHTOA. All right, and that tells us what sine, cosine, and tangent are. All right, I want to know, and then also for, well, let's just write it out. Sine of an angle theta is opposite over hypotenuse. Opposite over hypotenuse. Cosine of an angle theta is adjacent over hypotenuse, and tangent of an angle theta is opposite over adjacent. Basic trig. A lot of the trig that we use will basically just be this, right angle triangles. You also need to know the Pythagorean theorem. That is that a squared plus b squared equals c squared. That's a triangle, A, B, C. All right. What are the length of the unknown side? In order to find the length of the unknown side, I'll call this B. We'll say this is side A, and then this is side C. To find B, we use the Pythagorean theorem. That is that a squared plus b squared equals c squared. So B is equal to the square root of c squared minus a squared. That's the square root of 9 squared. Excuse me, to keep proper sig figs. Let's just say 9.0 squared minus 6.0 squared. The square root of that is square root of 45. Notice that actually it should be the square root of 45.0. Keeping one, no, I'm sorry, that's not true. It should be 45 because I get the square root of 81 minus 36, keeping 2 sig figs in that operation because there are 2 sig figs in 9 and 6. And then I take the difference in those two numbers, keeping 0 decimal places, just no decimal places, because there are no decimal places in those numbers. And then the square root of 45 is 6.7. So B is 6.7 meters. Um, that is, the side B is 6.7 meters. That's part A. Now in part B, I want to know what is the angle theta. All right, well, I know A, B, and C, so I can use any of these over here. I will just use sine of theta, which is opposite over hypotenuse. That's going to equal 6 meters over 9 meters. Notice that those units cancel out. The sine of an angle has no units. And then in order to find theta, I take the inverse sine of that. And that gives me an angle of 42 degrees. If you don't know how to do that in your calculator, then please come see me. I will show you. We're going to do it a lot, so please know how to do it. We want to know the sine of the angle phi. That is, what is the sine of phi equal to? Well, sine is opposite over hypotenuse. This is my angle phi. Opposite is going to be B over C. All right, so B is equal to 6.7, as we've already found. So that's going to be 6.7 over the hypotenuse, which is 9.0. And so the sine of the angle phi is 0.74. Remember, the sine of an angle has no units. 0.74, 42 is here. Now, just to do a check, I'll do this over on the side. If I do the inverse sine of 0.74, that should give me my angle phi. Inverse sine is 48 degrees. All right, now I've already shown that this is 42 degrees, and so this is 48 degrees. Notice that 42 plus 48 equals to 90 degrees. So the sum of those two angles have to equal 90 degrees, because in any triangle, the sum of all three angles equals 180 degrees. All right, so that's just a quick check. And then C, part C, want to know the tangent of the angle theta. Tangent of theta is opposite over adjacent. That's going to be 6 meters over 6.7 meters. And 6 over 6.7 is 0.90. Excuse me, not meters, just 0.90. And again, as a quick check, I can just do the sine, excuse me, the inverse tan of 0.9. And that should give me my angle theta. If I put that in my calculator, I find that it does give me 42 degrees. Which is what I want. Okay, so you're going to be doing a lot of trig in this course, especially when we do vectors and force diagrams and what have you. So there's quite a bit of trigonometry, but fortunately it's largely limited to right angle trigonometry and then also some basic geometry. So if you have trouble with that, then please come see me, and we'll deal with it in class as well, I'm sure. All right, estimate the number of ping pong balls that would fit into a typical size room without being crushed. In your solution, state the quantities you measure or estimate and the values you take for them. Okay, you should have a pretty good working knowledge of the different lengths that we use. What is a centimeter? What is a meter? And how can you compare those to real-life objects? So, like for example, on the exam, I'll ask you to estimate the area of the whiteboard or of your hand, or what is the volume of this room, something along those effects. So you just need to have a good measure of what is a meter, what is a centimeter. You need to have rough ideas of what is a kilogram, all the metrics, quantities that we will use. So this is a good example of an estimation problem. Just want an estimate of a typical size room and how many ping pong balls will fit in that room. Now, I'll consider a smallish room about the size of my office. That's 3 by 3 by 3 meters. That's about a 10 by 10 by 10 foot room. A room with 10-foot ceilings and 10-foot square on either wall. So like I said, a sort of a smallish bedroom. We wanted to estimate the number of ping pong balls that would fit into this typical size room. All right, so again, there are multiple ways you can do this. I'm just going to sketch this out. This is my room. It is a cube. Make it a cube to make that easier. And it is 10 meters by 10 meters by 10 meters. 10 by 10 by, or excuse me, not 10 meters, 3 meters. 10 feet roughly. So I have 3 meters, 3 meters, and 3 meters. It's about a 10 by 10 by 10 foot room. All right. And I want to know how many ping pong balls will fit inside that room. So I'm going to stack ping pong balls in this room, one on top of the other, all throughout the whole volume of the room. I want to know how many will fill that room. Now I'm going to imagine that these ping pong balls are actually little cubes. All right, and inside that cube you have your ping pong ball, because when you stack a ping pong ball, there's space in between them, and so you can imagine instead of stacking spheres that you stack cubes, right, and you get more efficient stacking there. So just for our estimate, we'll just assume that the ping pong balls are cubes, and I'm going to assume that they have a diameter of about 3 centimeters, or a length of about 3 centimeters. All right, so with those assumptions on the size of a room and of a ping pong ball, and that's really largely what you want to be able to do is sort of estimate what is the size, the volume, the area of a particular object that's common to you. Okay, so with those values, 3 centimeters for the ping pong ball, 3 meters cubed for the room, I want to calculate the volume of each of them. So the volume of the ping pong ball is going to be length times width times height. That's going to be 3 centimeters. And since it's a cube, I'm just going to cube that. That is 27 cubic centimeters. 27 cubic centimeters. Three times 3 times 3 is 27 cubic centimeters. And then the volume of the room is also going to be 3 meters cubed, so that is 27 cubic meters. Right. I want to convert one of these to cubic meters or cubic centimeters. I'm going to convert this value into cubic meters. There are 100 centimeters in 1 meter. I cube that, and I get 27 times 10 to the minus 6 meters. That is the volume of a ping pong ball in meters, in cubic meters. Now I just take the ratio of the two and figure out how many ping pong balls will actually fill up the room. So I say V room over V ping pong ball. That's going to be 27 cubic meters over 27 times 10 to the minus 6 cubic meters, and that'll give me a number of ping pong balls. 1 times 10 to the 6 ping pong balls will fill the room. So about 1 million ping pong balls to fill a smallish sized room, and that's probably actually a little bit of an underestimate because remember that we made that assumption that they were squares or cubes and not spheres, but actually they can get closer together if they're spheres. So it's a bit of an overestimate, but an underestimate, but it's an estimate nonetheless. All right, what is the volume of your body in cubic centimeters? Describe how you estimate this volume. The easiest way to do this is to draw yourself like this, and this isn't entirely wrong. It's actually a pretty good estimate. So we can draw ourselves like this. This is a picture of me. That's my body. I have some little bitty short nubby arms coming off, a little bitty head, and some little bitty feet coming off. So the bulk of my body looks like a cylinder. So we're just going to assume that our body is a cylinder. Let's just do some quick estimates. Say that I'm really tall, so I'm 2 meters tall, just to make the math easy. And then let's say that the distance from the middle of me to the side of me is 20 centimeters. That's going to be 0.2 meters. So I'm 2 meters tall and 40 centimeters all the way across. So I have 2 meters times 0.2 meters. This, as I said, this is a sphere, or a cylinder. So I can find the volume of that cylinder, pi r squared times h. That's going to be pi times 0.2 meters squared times 2 meters. That's my h. And that gives me a I want to convert these actually. So I'm going to go ahead and convert these to centimeters right now. So 0.2 meters is 20 centimeters squared, and 2 meters is 200 centimeters. And so that gives me my volume in cubic centimeters. I'm just going to estimate pi as 3 times 400 centimeters squared. That's 20 times 20 times 200 centimeters. And I estimate the volume on my body at about 240,000 cubic centimeters. Now, a better way to do this, some of you might have done this, but you can measure the volume of your body by displacement. So you take a container of water that you can be fully submerged in. You get into that container of water, and that causes the water level to go up. And the difference in the amount of volume that you measure of this amount of water will actually give you your volume. This is called volume by displacement. We'll do this in the lab later in the semester, and we'll talk about it. But the interesting thing is that, by design actually, that 1 cubic centimeter is equal to 1 milliliter. In fact, 1 cubic centimeter we often call just a cc. 1 cc is equal to 1 milliliter. So depending upon the amount of water that you displace when you go into a container, that is your volume. So according to our estimate, the difference between here and here in volume would be 240,000 milliliters, or 240 liters, as the total volume of our body. Right, analyze the dimensions of each of these equations. Are they dimensionally correct? For this, you want to know what are the units for each of these quantities. If you've had physics before, these are probably common to you. But let me just go through them, and you'll get to know them fairly well as we go through the semester. M is for mass. It's measured in kilograms. V and V naught are both for velocity. V naught is for an initial velocity, that is the velocity at time equals 0. It's in meters per second. G and A are both acceleration. That's going to be meters per second squared. H is a measure of height. X is a measure of distance. So those are both measured in meters. See, I think that's all. Yeah, so those are the units in these particular problems. And you'll need to know what are the units or the standards of measurement that we use for distance, time, mass, what have you. And these are what we use here: kilograms, meters, and seconds. All right, so for part A, I just want to put those units in for each variable. I leave off the constants, that is the half, and I'm just going to put in M. Just put in the units. M is kilograms. V is meters per second, but notice that that's squared, equals kilograms, meters per second, but notice that quantity is squared, plus the square root of M, which is kilograms, G, which is meters per second squared, and H, which is meters. So all I've done is I've replaced each variable with its units. Right? And now I have a jumble of things. I want to figure out, do the units match throughout? Now I see that the units match here and here, but I want to know, do the units match here as well? So I'm going to take this and simplify it. Plus, let's see, I have square root of kilograms and then this is going to be meters squared, and when I square root that, it's just going to be meters, and here I have second squared, and I square root that, and it's seconds. So you see, this is not the same as these two. So this is not dimensionally correct. All right, let's go to part B. X is in meters, M is in kilograms, and A is in meters per second squared. You will see a problem like this on the test, probably in the multiple choice. Make sure that you are very careful when you're putting in the units, because you see X is in meters, and then M is actually in kilograms. So just be careful of that, because sometimes people get confused. So meters, kilograms, meters per second squared equals M, which is in kilograms, and then V, which is in meters per second, but then it's the whole quantity is squared, so it's going to be kilogram meters squared per second squared. Now I'm just going to sort of combine some common terms. Kilograms, meters squared, second squared equals kilograms, and then I'll do this operation. So you see that is correct for both sides, so the answer is yes. And then finally in part C, I have V, which is meters per second, equals V naught. Again, V naught is just an initial velocity or an initial speed. We'll talk about that in the next chapter. So it has the same units. That subscript just means at time t equals 0, plus A, which is meters per second squared, times t squared, second squared. So I see my second squared cancel here, and while these two units might be the same, this is not. So the answer for C is no. Those are not dimensionally correct. All right, evaluate this derivative by two methods. By the chain rule to find the first result, and then use FOIL to expand the quadratic and then find the derivative. Just to remind you from class, the chain rule says this, that dx dt equals dx du times du dt. We'll use this a bit in this class as the semester goes along to do derivatives. You can also, we'll use it here for a quadratic term or for polynomials, but you can also use it for cosine trigonometric functions to do the derivative. It's actually pretty powerful. So this is the chain rule. If you're in differential calculus, it might be a few weeks before you get to it. Okay, so I want to take the derivative of this. Oh, let me also remind you that the derivative of a polynomial, that is, say, d dt of t to the a power is equal to t to the a minus 1 over a minus 1. So for example, the derivative of t squared with respect to t, or excuse me, not over a minus 1, I'm sorry, a times t to the a minus 1 is going to be 2t to the 2 minus 1, 2t to the first power. Okay, so I want to use the chain rule first. Now, my x is defined as this. X is equal to t minus 2 squared. U is this term. U is equal to t minus 2. All right, so dx dt then is going to equal dx du. That is d du of x is u squared. See here I have x is equal to t minus 2 squared, but if u is t minus 2, I just replace this term with u. So d du, u squared, that's the first part of my chain rule, times du dt, so d dt times u, which is t minus 2. That's the second part of my chain rule. All right, this is my dx du, this is my du dt. All right, if this is completely foreign to you right now, don't worry, it'll become more clear as we go along, but I just want to, some of you have already had this, I want to make sure that we're up to speed. Okay, so now Both of these are pretty simple derivatives. The du squared, that is the derivative of u squared with respect to u, is just going to be 2u. Right? And then the derivative of t minus 2 with respect to t is just going to be 1. Because the derivative of t is 1, the derivative of negative 2 is 0. And so this is 2u. And then putting back in my substitution is going to be 2 times t minus 2, which is 2t minus 4. So that's my derivative of that t minus 2 squared. Another way that we could do this is to do FOIL. T minus 2 squared is t minus 2, t minus 2. So that is equal to t squared. See, outer is negative 2t, so it's minus 4t plus 4. All right, so that's just expanding out that quadratic term, multiplying them together. And then I just say, what is the derivative of that term? T squared minus 4t plus 4. And that's going to be 2t minus 4. The derivative of 4 is 0. 2t minus 4. So you see that those two match. We'll be doing derivatives throughout the semester, so this is really just sort of the beginning. But they won't get much more complicated than this. All right, evaluate this integral. When you're doing polynomials, the integral of x to the a dx is equal to x to the a plus 1 over a plus 1. Right, so for example, the integral of x cubed dx is equal to x to the 4th over 4. X to the 3 plus 1 over 3 plus 1. Right, so we can do that here. We're going to have a slightly more complicated because we're going to evaluate it at certain limits or certain boundary conditions. The integral of t cubed, just like we did over there, is t to the 4th over 4 minus the integral of negative 4 is minus 4t to the 0 plus 1 over 0 plus 1 plus t to the 1 plus 1 over 1 plus 1. And then I'm going to evaluate this at an initial condition of 0 and 1. So let's just, I just sort of wrote out the terms here, but I'm going to simplify it a little bit. T to the 4th over 4 minus 4t plus 1/2 t squared. All right. When I evaluate it from 0 to 1, that means that my final condition is 1. My initial condition is 0. So I just say 1 to the 4th over 4 minus 4 times 1 plus 1 over 2. 1 squared over 2, actually. Just plugging in the values for t. So that's my final condition minus my initial condition, which is 0. So it's going to be 0 to the 4th over 4 minus 4 times 0 plus 0 squared over 2. Let's see, so that's 1/4 minus 4 plus 1/2. What is that? 1/4, that's 3/4. 3/4 minus 4. Is that minus 3 1/4? I think that's right. I don't have it written down here. All right. So we'll get to integrals in the next chapter, but they won't be more complicated than this, just doing basic polynomials. And I'll help you as we go along. We'll do some in class as well. All right, that's the end of chapter 2. Chapter 1, rather.